So welcome back friends. So we were looking at computation of simple process in QED. So we were looking at Compton scattering, the 4 simple process which we decided. So we are not doing explicit full calculations, we are finally doing the at least drawing the Feynman diagrams, and we know the methodology, and the basic idea is that you should be able to calculate these things using the Feynman rules essentially in a systematic fashion. So we looked so far at Compton scattering, and then we also looked at Bhabha scattering, okay, and we looked at it in pions as well as in electrons essentially. Now let us look at these 3 other diagrams, essentially what are the main diagrams which contribute at the leading order, okay, at the leading order we looked at. So for the Compton scattering we looked at the 2 diagrams, S channel and T channel diagrams. These are the 2 diagrams which we have loaded essentially, and then we saw what is the momentum difference and which is important, and we also gave the final results. I think it is equivalent to the Thomson scattering in the lowest energy limit essentially. In the low energy limit when the momentum can be it is equivalent to the Thomson scattering. Similarly you can do the same thing for Bhabha scattering. It will end up being equivalent to the Coulomb scattering actually, the Bhabha scattering in the low energy limit, okay, and these are all the trace theorems we calculated, we learnt about. And so the Bhabha scattering has the 2 main diagrams in this particular fashion essentially. So these are the only 2 diagrams. So in these both this process you have the S channel and the T channel. Now let us look at a very interesting process which is called the molar scattering. Molar scattering is scattering of an electron with itself essentially, with another electron, okay. So scattering of an electron with another electron. So the first thing, both the electrons have, both of them are electrons. You can do the same exercise with positrons also. You can do the same exercise, the answer is exactly the same because of the theorems involved essentially. Now these are like particles at the final states, you can interchange them essentially, and then so this is the T channel process. You can also have another diagram, it is also possible to have another diagram when the electrons are interchanged, they are identical particles. So also have, so at the vertex instead of taking, you take the P3 momenta, okay. So the other diagram is called a U channel diagram. So this is the first time we are seeing a U channel diagram, okay. So the molar scattering is given by these 2 diagrams. I advise you all try out these diagrams, check and verify whether you agree with these diagrams or not at your home essentially, check and verify. and let me know okay. You do draw independently. The rules I told you that there should be the charge also should be always be conserved. You should not violate any charge and Lorentz invariance essentially. Okay, these are the two main things. Okay, charge conservation and Lorentz conservation. So these two without varying, if you can draw any other diagram, let me know essentially, or if you either agree with these two diagrams itself, you let me know essentially. So this is a T channel process and this is a U channel process which contribute to the molar scattering. Okay. Now you can ask the question, what when you calculate this entire process, you get some amplitude, you get some d sigma by d omega. What happens to this process when we take positrons now there are various things which you can use essentially that in fact what happens is this channel this molar scattering is also related to Bhabha scattering by some symmetry called crossing symmetry. Okay, there is various things. Okay. Then E is equivalent to positrons, right, equivalent to electron scattering, electron molar scattering cross section. Cross section as QED interactions are C invariant, it's meaning they are charge conjugate invariant essentially. So that means if you replace electrons with positrons, most of the processes at the tree level the cross sections are exactly equal for most of the process. Okay, this is an important thing essentially. So somebody I think in the interaction section was asking me how can I treat positrons and everything for most of the meaning. So for the most of the process, okay, if you replace electrons with positrons, the cross sections are almost same, exactly same. Forget about higher order corrections for the tree level essentially. Basic QED process which we have listed of electrons are identical to those of positrons. That means in any process if you are bored of electrons and then throw them away and replace them with positrons, you do not have to do a fresh calculation, you can use the same calculation what you have done for the electrons essentially. This is because the S matrix is actually C invariant. That means the Lagrangian of QED is invariant when you replace electrons with positrons. Under charge conjugation symmetry, the Lagrangian is invariant, and this reflects in the cross sections. So this reflects in the cross sections. Okay. Okay. Now the other two processes which are equally important are, so let us draw the diagram. Essentially these two processes which are pair annihilation and pair creation. So pair annihilation is a process in which two electrons come, they annihilate each other and produce two photons. Now I asked a quiz why you need two photons essentially, why you need two photons in the final state essentially, why cannot you have just a single photon, why you cannot, the two electrons just give you two photons, why do you need to produce two photons? Now essentially you have the diagrams are very similar to the Compton scattering diagrams essentially, except that you have to invert them. Okay, you have to invert them in the sense, so we are writing time in the horizontal direction. So you have an electron coming in and a positron coming in, and this annihilates, gives you photons. So this annihilates and gives you photons essentially. So this is the annihilation diagram. Okay, two photons. So this is P1, P2 comes in, and this exchanges a momenta Q and gives you photons P3, P4. Okay. Now this is what channel of this diagram is this. This channel is T channel diagram. Essentially you see that it exchanges say it gives you two momenta are coming in, meaning P1 and P2 comes in, but what is exchanged is the P2 minus P1 or P3 minus P2. So this is the exchange of it's a T channel process essentially. Now again the two photons can be exchanged and you can interchange their momenta, and that gives you another diagram. Okay, so this is, and this always happens that the two electrons annihilate. Okay, electron and positron, a pair of electron positron annihilates and gives you two photons essentially. You cannot draw a diagram except the vertex diagram in which it's all virtual. Okay, the vertex diagram, the photon can be real, need not be real, it could be virtual. Okay, as you have seen that it is a propagator and everything. Here these are real photons. If you want to get real photons, okay, and the meaning that means these are exponentially observable, these two photons. In such a case you should produce two photons. So my question is to all of you, why does an electron positron pair annihilate to 2 photons. Why does it annihilate into 2 photons essentially? So, this is an important question, okay. And I will give you one clue, it violates some fundamental principles essentially. So, it violates some fundamental principles. I give you 1 or 2 lectures to think about it essentially. So, I am not giving you the answer. So, this will also be a part of the quiz. So, think about it. Clue, so let me know what is the fundamental principle which is being violated when an electron and a positron annihilate. This is a relativistic process, by the way. This is happens only in relativistic theories essentially. It does not happen in non-relativistic sense. Okay, this is a completely relativistic process, and okay, this is something which you should keep in mind essentially. The next process is the reverse of it, that it is a pair creation, that if you have 2 photons comes in, you produce they can interact and produce a pair essentially, a pair of electron positron pairs essentially. Now virtually remember that they can always produce electron positron pairs, okay, they can always produce electron positron pairs virtually with a single photon, but really if you want to produce, then it is requires 2 photons. Pair creation is just the opposite of these 2 diagrams, okay. You have gamma gamma Now, do we have a U channel diagram here? Okay, there is one more. Okay, now can you have a diagram in which there is an exchange, but you can exchange. I mean, you can have so at the vertex the momentum is changed essentially. So, you have P3 minus P1 coming in here, P3 minus P1, and this one is P3 minus P2. Okay. So, these are the 2 diagrams you can have. For pair creation and pair annihilations essentially. So, what we have seen the simple process in which the photon field is dynamical, which can lead to various, and all this process are QED process. We have seen some sort of diagrammatica. Okay, we have seen some sort of diagrammatica, and each of these calculations you have to do it. I don't nowadays, but at least one calculation you have to do it by hand, and remaining you can do it on a computer. using fine calc or any of this form or any of these process essentially. Okay. But one calculation, it is better to do it by hand. Good. Now that we have seen these things essentially, that in which the photon is dynamical, now so we can think of the properties, okay, in which the photon is not dynamical essentially. Okay. Let us think of some simple process in which when the field when we are dealing with particles meaning photon is not dynamical, can I still use this process and the processes are exactly the same, okay, and use the same process as before essentially. Okay. I will use the same process. Okay. So that is what we have seen. So far we have seen cross sections essentially, calculations methods for cross sections. What happens non-dynamical photon? So what I mean by non-dynamical, meaning let me qualify what I mean by this. That means I take potential to be static essentially. Okay. I take the potential to be static. So what I need to do essentially is that again I want to treat the potential to be some sort of a static potential, and you see the results are almost exactly the same, because you will get the same, almost the same results as you have whereas because the potential, if I take it to be 1 by r and you take the Fourier momentum of that, it just becomes 1 by k square, and you end up the Coulomb potential will be end up having the same results essentially. Okay. So let us do a formal solution. Okay. In what happens, so psi of x is equal to psi 0 of x plus E integral d power 4 y sf x minus y a slash of y psi of x. So psi prime of x is equal to, so this is again psi prime of x. So this is the most general solution. So but what we do is psi 0, okay, first what we do is we take psi 0, we take it as a free particle solution. Psi 1 is equal to psi 0 of x, then psi prime of x is equal to psi 0 of x E integral sf x minus y a slash psi of y d power 4 y, and this is also psi 0. This is free, this is free. So like I said, essentially we are always treating all the fields to be free particles essentially, we treat them as to be free particles. Okay. And then we have the next example as our next thing essentially. Now what happens if we have, what happens if we have a scatter essentially. So what happens if we have a Coulomb potential, say if we have a Coulomb potential. This is the example which is the most interesting example. So if we have a Coulomb potential, A mu is equal to again A0 A bar, A0 of x is equal to minus ZD by 4 pi mod y. So this everybody agrees because we know that is the nothing but your Coulomb potential essentially. Okay. So what we can do is essentially we can write your scatter equation, the scatter equation in this particular fashion: psi of x scatter is equal to psi 0 at the first order. Essentially we will come to the higher orders d power 4 y sf x minus y a slash of y psi 0 of y for first order. Now what we define is a scattering matrix, scattering, this is the same thing. The scattering matrix, this we have seen it as Fi is equal to final state as initial state. This I have mentioned it several times. Final state. In terms of this SFI, I can write, because given this wave function, this is a scattering wave function, scattered wave function. Now I can mod it, okay, I can mod it with the initial wave function. Essentially I can mod it with the initial wave function in the fashion as follows. Essentially SFI at leading order so this is your okay scatter, essentially SFI integral d power 4 y psi f bar of x sf x minus y a slash of y psi of y, where psi bar of y is equal to psi bar of x sf x minus y. So what we did was that psi bar of x is given by psi of x of y going to the scattering point, with a propagator. This wave is travelling to the propagating point as an interaction point. At the interaction point you add these wave functions, essentially a slash of y and psi of y. This is your propagator essentially. Okay. Now this is at your initial okay, at the initial point essentially. Now psi of y some normalization u of p initial state e power minus I p dot x, and psi final of y is also some free particle u wave function. This is exactly your, there is nothing different. Instead of same, incoming particle is u and outgoing particle is u bar, this is same thing, and a mu I take it as follows. Essentially this is the thing. Now you put back in your SFI this thing, okay. Now you put it back into the SFI, psi dagger, this entire thing, okay, this entire thing is nothing but just becomes psi of dagger of y. So this entire thing just becomes psi of dagger at y. So this gives me SFI at 1 at leading order is equal to I z d square by 4 pi some n normalization factor u bar pf sf gamma 0 u pi is a initial point integral d power 4 y mod y e power I pf minus pi y. Now this integral you can solve it d power 4 y mod y, okay, e power I pf minus pi y is equal to 2 pi delta ef minus ei times 4 pi mod q square. So SFI is equal to 2 pi I z square some volume factor m by ei ef square root of, these are nothing but your p0 wave functions gamma 0 u of pi si mod q square delta of ef minus ef. Now you see I have not made the photon field dynamical, I took a static photon potential and I still get propagator like 1 by q square term essentially. I still get a propagator like 1 by u square, and this gives me my differential formula. This gives me my differential formula d sigma by d omega is equal to z square e power 4 m power square 4 pi square u bar gamma 0 u mod square by q bar whole square. Now then you can use your stress formula and everything. This is exactly like what we have used for Feynman rules essentially. What we get for Feynman rules for the Coulomb cross section. Okay, when you do this Coulomb cross section, essentially you get back your the same thing, and now you can calculate it. You end up having d sigma by d omega is equal to z alpha square 2 beta square t square sine power 4 theta by 2 1 minus beta square sine square theta by 2. This is the famous Mott formula. And where beta is equal to p by e, okay, and q square is equal to pi minus pf whole square, that is equal to 2p square 1 minus cos theta. So in the limit beta goes to 0, you get back your Rutherford scattering. So the Mott formula is the relativistic correction to the Rutherford scattering essentially. The Mott formula is the relativistic correction to the relativistic scattering essentially. So in the limit beta goes to 1, essentially ultra relativistic limit, this formula is the same thing essentially, this remains the same thing. Okay, and if you do the same thing with the positron scattering, okay, if you do the same thing with the positron scattering, you will get the same formula essentially. At the leading order, it is the same as the electron scattering essentially. It is the same as the at the leading order, like I mentioned. So for the positron scattering, instead of U, you replace it with B bar, and U bar you replace it with UV, and the formula will exactly be the same, and the final answer will be the same essentially. So the final answer will be the same at the leading order. Okay, very good. So what we have seen is that, so the photon, even if you the relativistic version of Rutherford scattering essentially, where we have used the Green's functions methods, instead of using A as a dynamical field, but A as a potential itself, okay, as a Coulomb potential, and you see this gives you back exactly the same answers, because the potential, the static potential behaves exactly like 1 by q square, like a propagator essentially, because it is exactly like a propagator, and you end up having the same results essentially. You will end up having the same results. We will see one example of this in the next lecture. So we will do one scattering with proton scattering essentially. We will do one electron proton scattering. This is an example of a Coulomb scattering essentially in the next lecture, and then we will see some other theories other than electromagnetic theories, and then we move to higher order corrections, and finally we will close this lecture series with corrections to the hydrogen atom, relativistic correction to the hydrogen atom. Okay. So okay, so we will stop with this. Okay, we will do a recap of this, and then we will start the next lecture with electron positron scattering, Yukawa theories, and higher order corrections. With this, okay, thank you very much. Okay, thank you.